Hola amigos, we're back. We are looking at building general linear systems problems from real world contexts. Remember in the last video we discussed this descent path problem where we're in this, I don't know, maybe a Boeing 787. We're flying at 400,000 feet. At the beginning of the landing process, we mark that position along the ground. So if you were to project a shadow down onto the ground, we'll mark that distance from landing, the actual place we're going to land, as the 0 position. And then the claim is we're going to go from that 0 miles away from the landing spot along the ground, 40,000 feet, all the way down to landing 400 miles away, and landing will be at 0 feet altitude. I wanted to talk about, in the last video I made this claim that the way that we're going to do this is via cubic, and I wanted to talk about that choice. Basically what we're looking to do, if we were to erase the plane and kind of just think about the problem, we've got these two data points. We know where we start and we know where we end. I researched this for quite some time. Looks like 787s cruise at a certain altitude. When they're getting ready to land, they decrease their altitude. So let's assume that this is accurate. Suppose for a minute that I wanted to choose a linear graph. Linear graphs would just literally like connect it with a line. If I were to do so, the corresponding model that I would choose has two unknown parameters. Those are the mx plus b. So you might think of this as b plus unknown m times x. And in polynomial notation, we could call that like a naught plus a1 times x. However, I thought that this was really kind of a silly assumption, because what that means is like I'm going along and then all of a sudden I just literally like just start dropping immediately. And I felt like when I was in the plane, it seemed like a much more gradual process. With that said, I thought to myself like, okay, I'm not going to use the linear paradigm, which would have two unknowns that with these two data points would be completely determined. I could, of course, also, as I mentioned last time, use a quadratic paradigm, but I felt like quadratic, so imagine like connecting these with a parabola. I felt like that was even more ridiculous, right? So, you know, the parabola is kind of on two sides. So this is, of course, a piecewise function, right? A constant up here, and then I do a parabolic piece, and then I do a constant down there. But that's even more ridiculous, right? That means a gradual descent, and then all of a sudden I'm like speeding up my descent all the way to landing. No way is that going to happen. If I were to have chosen this, we would say that the height of the plane we could look at as, in the traditional sense, I think we used to call this like A, B, C. So that's the standard form that we learn in an introductory algebra class. In polynomial form, what we would say is, let's go ahead and reverse it from descending order to ascending order. We'd say maybe the constant c is a naught, a1, a2. And then we would say like, okay, this is plus a1 times x plus a2 times x squared. So that would be the model that I have. That would be three unknowns, but I only have two data points. But again, when I was thinking about that modeling type, it doesn't seem like it actually corresponds with the lived experience that I have on plane rides. The way that I would want to think about this much better is to think like, okay, we want to maintain this concept of smoothness both in the initial and in the descent, and a cubic polynomial allows me to do that quite nicely. Now, of course, if I were to continue down this way, the cubic polynomial would go down in that direction and go up in that direction. So I am kind of focusing on the most important part of that, which is the descent path. And that would allow me this gradual descension. And then eventually, as I descend faster and faster, I would decide like, okay, I want to slow that descent a little bit as I get closer to the landing path. And in this case, we'll just skip right to the general form of my polynomial. A cubic will have four unknown parameters. It will have the constant parameter, the linear parameter, the quadratic parameter, and the cubic parameter. And then each of those is assigned a corresponding value. So now I say that this is a naught plus a1x plus a2x squared plus a3x cubed. And so my real question that I'm asking here is, assuming that I want to use a cubic polynomial, how do I find the values of those coefficients to define this function, using the fact that I know these two data points and then I know kind of the shape of the graph that I want? a claim that I'm going to make is this is a general linear systems problem. Let's go ahead and take a look at what I mean by that. In order to fit the descent path of a plane, I'm going along at 40,000 feet. I come down, I kind of descend, and it doesn't really, right now I'm not talking about the rotation value of the plane. Like a plane can descend while it's kind of horizontal, right? I'm just talking about the global kind of pattern of this thing coming down to land. The fact that we choose a cubic polynomial as the model we're going to use for that path downwards gives us immediate information, which is I'm going to be looking for unknown values. In our work, we've been using kind of red to determine when things are unknown. The goal here is to find what values of these parameters fit the given path that we're assuming. We know more than that, though, however. We know not only that we want a cubic polynomial, we know that we want to start at 40,000 feet and we want to end at 0 feet altitude. And then we know that the total horizontal distance traveled is going to be about 400 miles. Let's go ahead and look at what this means. So we're going to impose our first condition. And our first condition verbally means that we start our descent, we start our landing process at 40,000 feet in the air. And we're going to assume that the beginning process is 0 miles. So we're going to kind of set our origin in terms of the number of miles traveled horizontally at the moment that we start our landing position. But that tells us that the value of x at that position is 0, and the output value, the height of the plane, is 40,000. Well, we know that if we put in 0 for x and p of 0 is 40,000, that actually results in an equation. And the equation looks something like this. 1 times a0, because there's a little 1 in front of that, plus x equals 0 times a1 plus x squared, 0 squared times a2, plus 0 squared times a3 is equal to 40,000. This is a linear equation. So our first constraint actually results in a linear equation based on the fact that I know the input and I know the output, and what I'm searching for is the value of the coefficients that satisfies that condition. Not only is this a linear equation, but we can write that as an inner product. So specifically, we see that this linear equation that comes from that condition is a row vector times the unknown but desired coefficients equals to 40,000. And here's a claim. This is actually a general linear systems problem. It has one row, right-hand side 1 by 1. Notice that I can actually write this. This is a 1 by 4. 4 unknowns, 1 by 1 vector. That is a general linear systems problem. The issue, though, is that it's not very well determined. Specifically, this tells me what the value of my first coefficient should be, but then I get full choice in values for my linear, quadratic, and cubic. It's not enough information to give me useful modeling context. In fact, I could set all of those to 0 and I would get a non-landing path. I'd just get a constant height, which doesn't give me any information. So even though I have a general linear systems problems, the one constraint that I have, the one condition, is not enough to kind of give me that really beautiful path that I'm looking for in the modeling problem that I started with. We might ask ourselves, after we have that one condition, is there anything else that we know? And we recall that indeed there is something else that we know. We know that at the end of the process, as we travel 400 miles horizontally, we want our height to be 0. We can formalize that observation as a second condition in our system, which means at the landing point, we want an altitude of 0. In terms of our function, it means p of 400 miles away from, in the horizontal direction, the moment that we started our landing process, we want that height to be 0. Well, that immediately tells me that at the x value at that point is going to be 400, the y value is going to be 0. This implies we can take our original model, substitute the value of 400 for x, put it in each place that I see x, and then set the entire thing equal to 0. When we do that, we get an equation that looks like this. 1 times a naught, because we always have a 1 out in front here, we can always write this as 1 times a naught plus x to the 1 times a1 plus x squared times a2 plus x cubed times a3. And then if we just evaluate x, those become coefficients. So now I have this linear equation that results from the assumption that we started with in our landing proposition. From there, that linear equation can be stored as another inner product. But remember that matrices and vectors are data structures. They're designed to allow us to store lots of information in an organized way. In other words, we can actually arrange our two inner products through matrices and vectors. We can store our first inner product, the first equation, the condition that we start at 40,000 feet, in the first row of a matrix, multiplied by the unknown coefficients in the modeling problem, and then I know that that whole thing should be 40,000 feet. And then I can store my second condition, my second equation, as the second row in a matrix. Those two equations combined act on the unknown coefficients that I desire to find to tell me, hey, whatever coefficients I choose, those should satisfy that when I start my descent, I start at 40,000 feet. And when I end my descent 400 miles away horizontally, I end at 0 feet. Now, probably you notice it's not possible for me to determine uniquely a cubic polynomial from only two constraints. I have 4 unknowns and 2 equations. There's actually an infinite number of polynomials that satisfy this. Now, we could go solve this problem, and in later videos we'll show what that actually means. But in this video, what I want to talk about is if I have a general linear systems problem with a short, wide matrix, it means I have more choices of my unknowns than I do constraints to help me solve for those. So of course I'm going to have an infinite number of solutions to this. We can use our modeling context to refine our equation set and actually determine a unique cubic polynomial, a non-singular linear system that exactly fits the data that we have. Let's go think about that problem for a second. So we're in this plane, we're flying along at 40,000 feet. We start our descent, we go all the way down to landing, and then we land very nicely. So far, we've introduced these 2 constraints. I'm going to introduce a third constraint, which is before landing, or at the moment that I start, I actually want my plane to be traveling horizontally. So there's this mark at which it's not like the plane is descending and then I restart my descent, or that I'm like somehow like coming up, then I go down. It's that at that moment, I want my plane to be traveling horizontally. Well, horizontal travel is actually a concept of a tangent line. So the claim that I'm going to make here is if I look at this path, on this side, I want the tangent line to that path to have a 0 slope, so that the plane itself is traveling horizontally at the moment that it starts descent. This results in a third condition, which we can write mathematically, or like a nerd. The tangent line to the descent path is horizontal at the start of the descent. What does that mean? It means that the plane is just traveling, not changing height when we start the landing process. Mathematically, that is written using this equation, so p prime of 0 equals 0. But we remember that the p of x looks something like this. It looks like this polynomial. When we take the derivative of that, we're literally going to take the derivative of a constant, that's 0. The derivative of x with respect to x is just the constant out in front. The derivative of x squared is 2 times x times that constant, and then here I bring down the 3, decrement the power, and then I get a function that looks like this, which means when I substitute in the 0 value for my x into the derivative of my descent path, and then I say that the output is 0, that results in a third equation. So everywhere I see an x, I put in 0, and that equation looks something like this. We can write that equation as an inner product. Notice here I've got 0 in the first column, 1 in the second column, 0 in the third column, 0 in the fourth column. That is now a row vector that stores that condition. I have my unknown scalar coefficients for my polynomial, a0, a1, a2, a3. And we say that that tangent path at the start of our landing should have a 0 derivative. It should have a horizontal tangent line at that point. That is yet a third condition that we can put into our matrix. And finally, not only do we assume that the tangent line at the start of the descent should be 0, but certainly if we want a nice landing, the tangent line at the end of the descent should also be 0. Don't you think? Wouldn't you much prefer the plane to land on this nice smooth path than to like come down and like bounce? I would. I hope that my pilot loves 0 tangent lines on the point of landing, right? That condition that we have, that path kind of follows the 0 tangent line, leads to an equation. Of course, the fourth equation that we look at, we can read as a nerd would. The tangent line to the descent path is horizontal at the landing point. In other words, the thing comes down and just kind of touches the tarmac very nicely. That condition means 400 miles away horizontally from the place that I started my landing. The derivative of my path should be 0. We already knew that my derivative for that descent path looked like this function. Everywhere I see an x, I'm going to put in the value 400, and then the output at that should be 0, which yields the following equation. Again, this is a linear equation that can be stored as an inner product. That inner product takes this form. We take each of those values, put it in the coefficient matrix. Our unknown scaling values for the polynomial that we desire is there. The output, the tangent line, has a 0 slope. And with that, the 4 conditions that we've imposed on our descent path lead to 4 equations in 4 unknowns. Those equations take this form. First condition is that I start my descent path at 40,000 feet. Second condition is after traveling 400 miles horizontally, I land at 0 altitude. Third condition is at the start of the path, I'm not changing height up or down. Fourth condition is when I land, I'm not changing height up or down. I have this really nice smooth touchdown to the tarmac. Once I have this set of equations, here's a claim. I can use the fact that each of these can be stored as an inner product to organize that information as a linear systems problem with coefficient matrix that arises from my modeling context, right-hand side vector that arises from my modeling context, and unknown coefficients that define my function that gives me the path that I'm looking for. So once I'm in this paradigm, we have now officially set up a general linear systems problems, and now we can use our approach of multiplying on the left-hand side by elementary matrices to solve this. But I want to make a point right here. Notice that this has already taken about 20 minutes of time to develop in a live in-class setting, and then this took me literally months of incubation time and thinking about to create all the graphics, to do the research, etc. This is what I say when I hate the word given. Most teachers don't do this because teachers don't get paid enough. So what we do is we create integer matrices that we give to students because those are the easiest to figure about. But the problem is most students want to see how this relates to their life. That costs energy. I do it because I'm crazy. I love this stuff and I want to share that love with my students. But I want to make the claim that when you hear the word given in a math class, I want to kind of do a little revolt against that. Nobody's ever going to give you a matrix that makes sense in the context of your life. Those are hard fought. In other words, if we plan to use linear algebra in live context, we have to be constantly searching, constantly thinking about how can I turn problems that I see in my life into linear algebraic structures that I can apply this analysis to. Throughout this course, one of the themes that I want you to see is that stuff is all around us. My job as your guide is to help you find ways to creatively leverage this material in your own world, and I believe you can. In the next video, what we'll do is we'll actually solve this linear system problem to uniquely determine a polynomial by applying Gaussian eliminations. I'll see you there.